All right, so let me read the question. It says, suppose f and g are positive functions. So I'm going to write that down. So I've got the info in front of me. So f, actually, let's make it a little easier. I don't need the f at x. So f is greater than 0 and g is greater than 0. So they give us that. Okay. And they say that f has a local max and g has a local min at c. So f has a max and g has a min at C. Okay, and we'll see how hopefully that information will be useful for us. And let's see what they're asking us to do. It says show that the function f at x over g of x has a local max at h equals c. Okay, so the function we're working with is h at x, which is f at x over g of x. Okay, and I need to show that it's a local max at c. So what I want to do is I just want to make sure I'm clear as to what it is that I have to show. So in order to look for local extrema, I'm looking at the values where h has a derivative that's either 0 or does not exist. And we need to show that the derivative changes sign at that point. Okay. And we're going to assume that any values where it doesn't exist, we're only talking about values where the original function exists. Okay, so it's sort of an unwritten rule here that although here we don't have to worry about that, I just realized because g of x is greater than 0. So we know g of x can never be equal to 0. So that's kind of helpful. We don't have to worry about that. Okay, but this is the two things we have to show. We have to show that h prime at c is equal to 0 or does not exist. Okay, and we have to show that at c, the derivative h prime has to change from, so since we're looking for max, it has to change from positive to negative. So these are the two things we have to show. So I'm going to start by finding the derivative. Okay, so h prime of x is derivative of the numerator times the denominator function minus numerator times the derivative of denominator all over g squared. Okay, and here, this is where we're going to use that f and g have a max and a min. Okay, so here I'm going to say that this is equal to 0 or does not exist. Now we have to justify why that's the case. Well, f has a max, therefore f prime is equal to 0 or does not exist. So if f prime doesn't exist, this whole thing won't exist. Okay, and f prime is equal to 0, then we know that this first part is just going to be 0 times whatever g is, 0. Okay, now done. Let's look at g. G has a min, and so that means g prime is equal to 0 or does not exist. So again, if it doesn't exist, the whole thing won't exist. But if g prime is equal to 0, then here I have whatever f is times g prime, which is 0, and so equal to 0. Okay, so we have shown that there's a critical number for h, okay, at c. Okay, any questions on that part? All right. The next thing I have to do is I have to show this change in sign. Okay, so I'm going to draw myself a number line, okay, for h prime. I'm going to give myself a lot of room because there's a lot of things going on. So let me look to the left of c. Well, here I'm going to go back to the fact that f has a max. So if f has a max, that means f prime at c goes from positive to negative. And since g has a min at c, it goes from negative to positive. And I'm going to use this information along with the fact that f and g are both positive to determine the sign of the derivative to the left of c. So to the left of c, f prime is positive. Okay. G is always positive. Okay, minus, F is always positive. Oops. And then G prime on the left of C, because there's a min there, is negative. And obviously the denominator is just positive. I don't have to worry about that because it's squared. So here, what do we have? We have a positive number, and I'm subtracting a negative number, which is the same as adding a positive number. And so there we go. To the left of C, H prime is positive. Let's now look to the right of C, and I'm going to do something very similar here. Okay. F prime to the right of C is negative. Okay. G is always positive. Okay. Minus. Okay. G again is, F is always positive. And G prime to the right of C is also positive. Okay, and the denominator I don't need to worry about because it's just some positive number because it's being squared. Okay, and so here, what do we have? We have a negative number minus a positive number. And of course, what happens when I have a negative number and I subtract, say, 3 or 7 or 9, it's just going to get smaller and smaller. There we go. So we have shown that H prime at C is equal to 0 or does not exist. And H prime goes from positive to negative at C. Therefore, H has a local max at C. Okay. And what we see here is a much more involved version of some of the other questions that we've solved. Okay. But it's about understanding what it means for F and G to have maxima and minima and how their behavior changes around C, and then applying that to how F over G behaves to the left and to the right of C. Okay, so nice question. All right, any questions on this that we want to ask? Is there any part of the question that you want to ask about? No? Okay. So again, fairly involved, but in the end, when you think about it in small bits, I just used all the information that we've been learning about, just not with a specific function. All right. So if there's no questions, I'm going to move on to page 206, number 10. Let's see what that gives us. Okay, 206, number 10. Okay, so page 206, number 10. All right, so here they're asking us to find constants a, b, and c for this function, which I'll write down. So f at x is equal to ax cubed plus bx squared plus c. And it has a local extremum at 211. Okay. And a point of inflection at 1,5. Okay. So here we've seen this type of question before. Since it has a local extremum at 211, and keep in mind that this is a polynomial, so I don't have to worry about the derivative not existing. And this tells me that f prime at 2 is equal to 0. And here, if there's a point of inflection, we know that the second derivative is going to have to be 0. Okay, f double prime at 1 is going to be equal to 0. Okay, so here are my here's all my information, and of course keep in mind that these 2 points are also on the function. Okay, but as we've seen before, I'm not going to start with the original function, because when I take the derivative and the second derivative, I'm going to get simpler functions to work with. So make sure you're checking my algebra here. So here we have 3ax squared here plus 2bx, and then the c derivative is 0, and then the second derivative is going to be equal to 6ax plus 2b. Okay, so in the end, both derivative and second derivative are, about as complex as the other, but I'll start with the second derivative since there's no squares involved. And so now I'll find my first piece of information. So we saw that f double prime at 1 is equal to 0. Okay, so here f double prime at 1 is going to be equal to 0. So 6 times a times 1 plus 2b. So we have 6a plus 2b is equal to 0. And there's sort of my first equation. Okay, now I could solve for b in terms of a, or keep it and maybe use elimination depending on what happens, but this is pretty easy here. So that's a negative 6a divided by 2, so negative 3a. All right, now let's go to the second piece of information, that f prime at 2 is equal to 0. So f prime 2 is going to be equal to 0. And now I'm just going to replace 2 here. So 3a times 2 squared plus 2b times 2. So here, what do we have? We have 4 times 3, 12a plus 4b is equal to 0. And when I solve for b, if I bring the 12a to the other side, negative 12a divided by 4, I see that b is equal to negative 3a. It's the same piece of information. So that means this is not going to give me any more information than the other. Okay? So this might seem like a problem, except that I have two other pieces of information. Remember, I also know that these 2 points are on the function. Okay, so while this might seem like a bit of a stumbling block, I have 2 more pieces of information I can use. Okay, so this is where now I'm going to start using these points. So when x is equal to 2, y is equal to 11. So let's stick in x equals 2 here. So we have a times 2 cubed. Okay, plus, now I'm not going to put in b here because I know that b is equal to negative 3a. So I might as well bring that into the picture. Okay, times, where was I? 2 squared plus c. And here we were working with 2, so that's going to be equal to 11. So let's clean this up a little here. So it looks like this is going to be 8a. This is going to be minus 3 times 4, 12a plus c is equal to, and that I believe was 11. I'm not quite sure why nobody piped up on that. Okay, so please make sure you're checking my work here. So what do we have? We have negative 4a plus c is equal to 11. Okay, so that'll be my first equation because I think the other one's just going to give me a second equation in a and c. So now I'll input 1 into here. So these are just both going to be 1 since 1 cubed and 1 squared is 1. So I'm just going to have a plus b, which is negative 3a, plus c is equal to 5. And if we clean this up, 1 minus 3, so negative 2a plus c is equal to 5. And there's my second equation. All right. And now I'm going to solve this using elimination since I've got the c's there. So I'm going to subtract 1 minus 2. And what do we have? We have negative 4 plus 2 is negative 2a. C minus c is 0. And then here we have 11 minus 5 is 6. So it looks like a is going to be equal to negative 3. Okay. So there's one of our solutions. I know that b is equal to negative 3a. So negative 3 times negative 3. So it looks like b is equal to 9. And then finally c, I'll pick any one of these. So I'll take this one here. I get c is equal to 2a plus 5. So 2 times negative 3 plus 5. So it looks like c is equal to negative 6 plus 5, negative 1. Okay, so that seems to be our 3 values. Okay, So this one here was a little different from the ones that we'd solved, because normally the first and second derivatives end up being useful. In this case here, they just happen to produce the exact same relationship. So that's why I needed to then use both points. That then allowed me to find the rest. Okay, any questions on this? All right, okay, so if none, let's head on to the questions on page 216. All right. So for few people asked for page 216 9b, and there's a slightly more interesting graphing question I was going to do. So if somebody asked that who's here, maybe in the chat, just kind of tell me what the issue was. Because once you find A and B, does anybody need to do 9A? Let me just do a quick check. Anybody need 9A here on page 218? Okay, so the 9B, I would say, if I don't have time to get to it, with the graph, just use Symbolab to find the first and second derivatives, and it should be a fairly straightforward function to graph, okay? But if somebody needs 9A, let me know, I can do that later. So let me get on to 11A. Okay, so this is page 218, number 11A. All right, so here 11A says determine the conditions on the parameter K such that the function f will have critical points. Okay, so let's write down the function f. So we have f at x equal to 2x plus 4 over x squared minus k squared. All right, so here they've given us this function that has an unknown in the denominator, and I already forgot the question. F has to have critical points. All right. Now, one thing about rational functions is that rational functions are differentiable everywhere they're defined, something we would have talked about earlier on. So obviously there's going to be values at which we may have vertical asymptotes, okay? But otherwise, they are smooth functions wherever they're defined. So we don't have to worry about, where the first derivative doesn't exist, but we do have to worry about where the first derivative is equal to 0. So essentially what we have to show is what values of k allow the first derivative to be equal to 0. This is going to be our task if we want to have critical points. All right, so see where it goes. Let's start by just taking the derivative. Okay, so here again, please make sure you're checking my work very carefully, because any small sign error will change the problem. Okay, so derivative of the numerator is going to be 2 times the denominator function, so x squared minus k squared. Okay, minus, next comes the numerator function, so 2x plus 4. Okay, times the derivative of the denominator function, which is just going to be 2x because k is a constant, so k squared is also a constant. All right, and so all of this over x squared minus k squared, all squared. Okay, so our goal is to determine what values of k allow this derivative to be equal to 0, because that's what you're going to need to have critical points. And we've certainly seen derivatives of rational functions that can never be equal to 0. And we've seen lots of rational functions that don't have any local maxima or minima, or even any critical point, points of inflection. So there's no guarantee that the numerator is going to be equal to 0. All right, so let's see what happens. Again, we don't necessarily worry about where this is going. Let's just apply what we know. So I don't have to worry about the denominator. Since it's a fraction, it's only the numerator that needs to be 0. So let's simplify this a bit. So here we've got 2x squared minus 2k squared. And here we have minus 4x squared. And then here it looks like we've got minus 8x. Okay, again, please make sure you're checking that. And what I notice here is that what I'm left with is some sort of quadratic expression. Okay. And so here, what do we have? Let's clean this up a bit more. We have negative 2x squared minus 8x minus 2k squared. Notice how I put the 2k squared last, because that's just a constant. So this is like my C value, if you think of it that way. Okay. And here, to make our lives a little easier, let's divide both sides by -2 to simplify this. So here, if I divide this whole thing by -2, I end up with x squared plus 4x plus k squared equals 0. Okay. So this is where now we have to figure out. We've kind of gone as far as we can in terms of the algebra. So this is where we have to ask ourselves. This function, think of it as a quadratic function, needs to be equal to 0. Okay, and this is where we need to kind of think back to a neat little trick you would have used back in grade 10, grade 11. Maybe we haven't come up to it at this point here. But remember that when you have a quadratic, and it does have a positive leading coefficient, there's no guarantee that there's going to be zeros. So there might be zeros like this, you might have a single 0. Okay, but remember that you also have quadratics that are never equal to 0. Okay. And so you think, well, wait a minute, how can we find these x-intercepts? We can certainly use factoring, although there's no way I'm going to be factoring with a variable in it. The other option is the quadratic formula. Okay. And you know that in order for it to be 0, that portion that's inside, think of the quadratic formula. This portion inside of the square root cannot be less than 0. That if this portion inside the square root is less than 0, then there won't be any x-intercepts. So in order for this quadratic to have x-intercepts, the discriminant, the b squared minus 4ac, has to be bigger than or equal to 0. Okay, so this is what we need to show. We need to show that, and again, think of this as, a is 1, b is 4, and here c is the k squared. Okay, that b squared minus 4ac has to be bigger than or equal to 0. It can be equal to 0 because it just doesn't say it has to have 2 critical points. It needs to have at least 1. And so what's b squared? So here we've got 16 minus 4 times your a value is just 1, and your c is k squared. This has to be greater than or equal to 0. And what we notice here is that I'm just solving a quadratic inequality. Okay, except the variable in this quadratic inequality is this k. So I need to find the k values that make this expression greater than or equal to 0. And we know how to solve this. Since it's a quadratic, I can't just solve for k explicitly. I need to factor. So let me factor out of 4. So I'm left with 4 minus k squared. And this is a perfect difference of squares. So this is 2 plus k times 2 minus k needs to be greater than or equal to 0. And since this is a quadratic with a negative leading coefficient with x-intercepts at 2 and -2, I know that this is what the graph's going to look like. So where is this expression greater than or equal to 0? In the interval 2 to -2 inclusive. So that means that k needs to be less than or equal to 2 greater than or equal to -2. And there's my answer. So a bit of a journey here, but think about what I did. I started off by identifying what I needed to show. I needed to show when the derivative could be equal to 0. So I took the derivative, set it to 0, simplified as far as I could, and then I realized I was left with a quadratic equation. And the only way for this quadratic equation to have solutions is for the discriminant to be greater than or equal to 0. That if this was less than 0, there can't be any solutions. Whereas when k is between -2 and 2, inclusive, this expression, that is my discriminant, will be greater than or equal to 0. Hence, this has solutions. Okay, so again, nice problem because, a bit of a journey, and we had to use a good old trick with the discriminant. Any questions on this one here? No? Okay. So the next thing I've got on my list is number 13. Okay, so let's take a look. Hopefully I've got enough space. So this is page 218, number 13. All right, and let's see what that's asking. It says determine the critical numbers and the intervals on which the function g of x is increasing or decreasing. All right, so let's do g of x is equal to x squared minus 4 squared. And we need to determine critical numbers and increasing and decreasing. All right, so both of these things are going to involve the first derivative. So let's find the first derivative. Okay, so here I'm going to have to use the chain rule. So derivative of u squared is 2u. And then times the derivative of u, so 2x. Okay, so if this needs to be, since we're looking for critical points, again, it's a polynomial. We don't have to worry about the derivative not existing. So we need to determine where this is equal to 0. And it's already partially in factored form. And I say partially just because x squared minus 4 can be factored even further. So here 2 times 2 is 4. We've got the x. And then, of course, x squared minus 4 can be written as x plus 2, x minus 2. Okay. And so this is 0 at 0, 2, and -2. All right. So let's create our number line. All right. And let's examine here that we've got a cubic polynomial with a positive leading coefficient. So I don't need to be sticking numbers into here. I can just draw my sketch of the cubic with these zeros. And so here we have negative, positive, negative, positive. Okay. So our critical numbers are just 0, 2, and -2. Okay, so I'm just answering what they're asking me for. And the next thing they're asking me for is intervals of increase and decrease. So let's do increase. So what are our intervals of increase are wherever the first derivative is positive. So here we have -2 to 0, and then we have 2 to positive infinity. Notice I'm using interval notation, and then for decreasing, here it's wherever the first derivative is negative. So I have -infinity to -2, and then union 0 to 2. Okay. So this one here, fairly straightforward application of what the first derivative is asking, is what information the first derivative gives me. Notice here, they didn't ask me for the local extrema. So here, obviously, we notice, the derivative goes from negative to positive. I would have a local min here from positive to negative, a local max, negative to positive, another local min. But, don't give more information than they're asking for. This is exactly what they're asking for. Okay, any questions on this one here? Nope. All right, so the next thing we have is number 2 on part C of the assignment. Okay. So here, I'm not sure if people want me to do the sketching part. I can do it since a few people online asked, so I will do the sketching part. I'll try to do this as quickly as possible. All right. But I think we're gonna focus in more on part B. Okay, so this is unit 3 assignment, part C. All right, so we want to find, oh, we also have to sketch the acceleration function. Okay, well, okay, I'll try to do this. If that's, I didn't realize that the graph 2, so I'm going to take 2 different colors to do that. All right, so the acceleration function, we'll start with that. So I know to find the derivative of the velocity function, which is going to be the acceleration function. Okay, so I'll do this in red. Okay, we'll start by determining where the derivative of the velocity is 0. So here we see we have a horizontal tangent, and we have another horizontal tangent there. So here we've got zeros at these values here. Okay, and now I can start doing my analysis. So if I'm going to the left of this point, I see that the derivatives are negative and getting more negative. So they're going to do, something like that. Okay. Then here, the derivatives are now going to be positive and getting more positive. Okay. So I'm going to what am I doing here? I need to find the derivative of this function, so I'm going the other way around. Okay, so here we see that slopes of the tangent are positive, and they're getting more positive till about this point here. At around this point, I see that the tangents are starting to get less steep. So this is going to reach sort of like a maximum value somewhere there, and then the derivatives are going to get less positive until I get to this point here. Okay, something like that. And then I see that the slopes of the tangents are getting negative and more negative. Okay, so this here would be an idea of what the acceleration function would be. So this is the acceleration function, which of course is the derivative of the velocity function. Okay. So now let's go to the more interesting one, which is drawing the position function, or a version of the position function, because there are many. All right. So here, again, I'm going to focus on where the derivative is 0. But of course, now I'm talking about the derivative of the position function, because the velocity, of course, is just the derivative of the position function. So this tells me that at this value here, the position function is going to have a horizontal tangent, but the derivatives are going from positive to negative. So that means there's actually going to be a local minimum there. So I'm just going to pick some random point. Okay, at this point here, there's going to be a horizontal tangent, and to the left, the derivatives are going to be positive and getting more positive. Okay, because you look at the slopes of the tangents and you see they're getting bigger, as we see here. Okay, now the derivatives of the function are now going to become negative, and they're becoming more and more negative till about this point here, where they're going to reach their most steepest. Okay, so here they're getting steeper, 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 and somewhere there, now they're going to start getting less steep. Okay, because it's getting less and less negative until eventually at this point here, I'm going to have another local extremum, except now it's going from negative to positive. So it's going to be a local minimum. So somewhere along there, okay, now you see the slopes of the tangents are getting less steep. There we go. There's my local minimum. Okay. Similarly here, now the velocity is positive and getting more and more positive. So that means my position function, the slopes of the tangent, are going to be getting steeper, 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 steeper till about there. And then at this point here, they're going to start getting less steep until they reach, let me draw a little line. So now they're getting less steep, we see, until eventually the slope of the tangent is 0. And now the derivatives are becoming negative, hence the slopes of the tangents are becoming negative, something like that. Okay. Now, from the look of it, it's not too surprising because when you look at the velocity function, it looks like a cubic. Its derivative, the acceleration function, looks like a quadratic. And the original position function looks like a quartic. So its derivative would look like a cubic. So this kind of all fits with what we would expect based on the shape of this graph. Okay. Any questions on this part here? No? Okay. So now let's go on to this question. It says, estimate when the object is speeding up and slowing down. Okay. Now, I already have, the derivatives and the original, not possibility for the original position function. Okay, but I could have done this question just with the velocity function. So what do we have to show in order for an object to be speeding up? So let's just remind ourselves what we have to show. An object is speeding up if the velocity and the acceleration have the same sign, and it's slowing down, okay, when the velocity and acceleration have opposite signs. Okay, so I can work with the graphs, or I can even just work with the velocity function. But let's start with speeding up, okay? So I notice here that and actually I will have to work the velocity function because my acceleration function doesn't go all the way down. Okay. So here, I look at this section here where the velocity is positive. Okay. But look at the slopes of the tangent, which would be the acceleration. So here, velocity is positive, but acceleration is negative. So this would not be part of this. In fact, we can start our slowing down. Yeah, so it looks like from about, what is this? 0 to, I don't know, this is about 0.2467 to 0.07. We're slowing down. Okay, now let's see what's happening in this section here. In this section, the acceleration is still negative, but so is the velocity. So in this section here, we see that velocity is negative and acceleration is also negative. But then in the next portion, I see that the acceleration, okay, which is the slopes of the tangents, which what you see here, is going to change sign. So now in this section here, velocity and acceleration have the same sign. So I'm going to put that in this category here. So it looks like we've got 0.7, oops, 0.72. This looks like to be about 1.1. Oh, sorry, 2.1, 2.1. All right. So now let's go to the next section here. Velocity is still positive, but the acceleration now, look at the slopes of tangents, they're positive. So in this section here, we have velocity negative, acceleration positive. So that's going to go in the slowing down section. So this here, we've got 2.1 to about 3.4. Okay, And I'm just going to do this now throughout. Okay, so now here I see that the velocity is now positive and the acceleration is still positive. So it's till about here, they're both positive again. So here, acceleration positive, velocity positive. So in this section here, it's going to be speeding up. So from about 3.4 to about, looks like this is 5.8. It's going to be speeding up. Okay. And now finally in this section here, or almost finally, we see that the velocity is positive, but the acceleration, look at the slopes of the tangent, are now negative. So this is going to go into slowing down again. So union. So this is 5.8 to, this looks to be about 7.2. And then finally in this last little bit, okay, the velocity is positive, the slopes of the tangent, the acceleration, sorry, the velocity is negative and the acceleration is negative. So that's going to go in the speeding up category because the signs are the same. So this looks to be about 7.2 to 246 to 7.6. And there we go. There's our speeding up, slowing down. In a lot of ways, it's almost easier to do it with an equation. Okay. I guess what I could have done also is made a number line, but I wanted to show you the relationship between the behavior of the velocity, positive, but the behavior of the acceleration, you have to look at the slopes of the tangent, negative. Okay. Any questions on this one here? Oh, I'm just looking at the answers I got. And, you see the numbers I used in my answer are slightly different, but that's because I'm estimating on a graph. So, instead of calling this 7, I called it 0.75. That's close enough. Okay, any questions on this here? No? Okay. So let's move on to this graphing question. Okay. Now, again, that question on 9B would just be another version of this. You could, like I said, you can just look up on Symbol Lab to get the derivatives, but let's see how this would work out. All right, so I'm going to start. Step 1 is going to be everything I can get from my function. Okay, so I'm going to focus on this equation here, and I see that my domain will have one restriction. So the domain is all real numbers, but I'm going to eliminate 1. Okay, here I have one x-intercept. The numerator is going to be 0 at 0. Okay, and so the y-intercept, okay, if I input x equals 0, will also just give me 0. So it passes through 0, 0. Okay, next let's look for our vertical asymptotes. Okay, and the only one I'm going to have is at x equals 1. All right. No holes because there's nothing that's going to simplify from this here. Okay, my end behavior. Well, this one's pretty easy because when I look at the numerator, it has a degree of 1, whereas my denominator, if I were to multiply this out, I'd get an x squared in the denominator. So I have degree 1 over degree 2. Since the denominator is a higher degree, we know that the limit as x approaches both positive and negative infinity is going to be equal to 0. So we have a horizontal asymptote at 0. All right. And now finally, let me make my number line for the sign of f. And the only two places where the sign can change are at 0 and 1. Where it's equal to 0, where we have a vertical asymptote, the denominator, notice, is always positive. So here at -1, the numerator is negative, so negative. Between 0 and 1, the numerator is positive, so positive. And 1 to infinity, again, the numerator is positive. If I pick, say, x equals 2, so positive. All right. Any questions on this analysis? Okay. Now, keep in mind here, when I had to do end behavior, I had to take a look at what would happen if I, expanded that denominator to get a sense of what my end behavior was going to be. No, okay, so let's move on to the derivative. So I'm not sure how much, see if I can have enough space to go vertically here. No, I mean horizontally, so 2. So now the derivative, now we've already found the derivative. So in order for the derivative to be equal to 0, I just need the numerator to be equal to 0. So in other words, that's at x equals -1. Okay, now I know that my derivative doesn't exist at 1, but I also realize that it can't be a local extrema, but I'm still going to include this on my number line, okay, because it will give me information on when the function is increasing or decreasing. So now f prime, I'm going to determine its sign, and we have to look here at -1 and +1. Those are the only two places it can change sign. Okay, now here I do have to be careful because the denominator is being cubed, so I do have to take it into account. So let's see if I take -2. So -2 plus 1 is negative times negative, so positive in the numerator, and -2 minus 1 is a negative number, cubed is still negative, so it looks like it's negative on that side. Okay, let's pick a number between -1 and 1. How about 0? This is positive times negative. It's negative. Okay, 0 minus 1 is negative. When I cube it, it's still negative. So we're going to end up with positive. And then finally, here, if I take 2, positive times negative over positive cubed is going to be positive. So it looks like this is going to be negative. All right. So now from here, we can see that we're going to have at -1, the function is going from, derivative is going from negative to positive. So in other words, from decreasing to increasing. So it looks like I have a min at -1, and I need to put this into my function to determine the value. Now, of course, we can do this in our heads, but I don't want to take any chances. So here, what do we have? We have, what was it, -1, so -5 divided by, and what do we have in the denominator? -1 minus 1 all squared. So it looks like -1.25. Okay, and there's my min. Now, I'm going to do the same thing for the second derivative. So here, the only place the second derivative is equal to 0 is at x equals -2. Okay, but of course, as before on my number line, I will also include 1. Okay, so I can get an idea of concavity. Okay, now look at that. The denominator is to the power 4, so it's always positive. So I only have to look at the numerator. So the numerator here, if I take -3, -3 plus 2 is negative, so the whole thing is going to be negative. At 0, positive, the whole thing is going to be positive. And here, say 2, whole thing's going to be positive. So my concavity is down, then up, but this means that I have a point of inflection at -2. Okay, and let's stick that into my equation here. So we have 5 times -2 and divided by -2 minus 1 all squared. So negative around 1.1. Okay. And so now we have all the information that we need. So I'm just going to grab a ruler and try to set up my graph. Okay. So let's take a look at my x values. So I have an asymptote at 1. I have an x-intercept at 0. And then my minimum and point of inflection are at 1 and -2. So that means I'm going to put my y-axis a little off to the right so that I've got more room on the negative side. Okay, and given the numbers, I'm just going to go up by 1 per box. Okay, whereas my y values, well, you see the y-intercept is 0. Okay, I have a horizontal asymptote at 0. And so most of the action is happening on the negative side of the y's. So maybe I'll do the same thing here. I'll go a little, maybe I'll do this because I do want to leave myself a little bit of room to draw it out. Maybe I could have gone up one more. Sometimes you make a choice, you don't worry too much about it. Okay, and so here, so these for sure, I'll go up 1, 2, -1, -2. Okay, I might have enough room to go further, but we'll leave it at that. All right, and now for the y, so since I got -1.25, I might do 1, 2, 3, 4. So that's -1. So that -1.25 is just the next one down. Okay, sometimes use your fractions to help you out here. So I know I've got my, my horizontal asymptote at 0. I've got my x and y intercept at 0, 0. At -1 and -1.25, I've got my minimum. At -2 and -1.1, somewhere there's I've got my point of inflection. And then at x equals 1, I have my vertical asymptote. Okay, so I'm going to deal to the right of 1 because I think that's actually kind of easier. So I know that the function is positive, I know that it's decreasing, and I know that it's concave up. So the function is going to have to look something like this. So concave up, decreasing, and positive. Okay. Okay, so that part's done. Okay, now here I've got my minimum. Between 0 and 1, the function is positive, so it has to go to positive infinity here, the vertical asymptote. And I see that it has to stay concave up all the way up to -2. So I'm going to try to make sure, as I'm drawing this, make sure that it looks concave up the whole time. Okay, so this is where sometimes it's easier to just flip it around. Okay. And make sure it looks concave up the whole time. It looks a little funny here. So I might just fix that a little bit. Okay. There you go. That's maybe a little bit better. Okay. Still looks a little funny, but that's not too bad. Okay. And now from this point forward, it's going to have to be concave down, and it's going to have to approach 0. So this is where, it's a little, you're going to try to make it look concave down, and you want to make sure it approaches 0. Okay. So something like that looks reasonable. Okay. And so here we have presumably what our graph kind of looks like, and it satisfies the conditions. And by plotting the points very clearly, it helps guide me on graphing things like concavity. All right. So any questions on what I did here? Okay. So notice how I set up my solution so that all the information is very clearly shown, but very briefly shown. There's no need to really give any explanations. It's just about showing all the important aspects. And then from there, setting up my graph with any asymptotes and any special points, and then following. And you see, I didn't necessarily have to use increasing, decreasing too much, because in this case here, the concavity was a little more helpful. It depends on the function and what portions of it that you're drawing. All right. Just trying to think, is there anything else to be said about graphing? So you got to think that when, I really took my time, a lot of this stuff, you're not going to be explaining it as you're writing it down. So a question like this, with the derivatives all given, you should be aiming at about, 10 to 12 minutes maximum per question. That's what you should be aiming for. Okay. What about to the right of the vertical asymptote? Oh, we dealt with that here. That was the first thing that I did. I saw that the function was positive. It was, so that's why here it had to go to positive infinity. It's got to approach 0 as x gets very, very large, but it can't ever cross the x-axis because there's no other x-intercepts, and it has to be drawn as concave up. Okay, does that answer the question? Oh, yeah. No, we're not being picky. Yes. So somebody's asking like, how picky do you have to be about? No, we're not going to be picky. What we are going to be picky about is those special points where things happen, like maxima and minima and points of inflection. There's no need to start plotting other points. Okay, for sure. I just drew it so that it satisfies the conditions. Okay, because usually the most important things for us are where these special things are happening and what the end behavior is. Okay, if you needed anything specific at any one point, you could always just calculate it. Okay, so that's a good question, Nicholas. No need to be that precise on where you're drawing things. Okay, does that answer the question? Okay. All right. Anything else about this here? Okay, so I'm going to stop the